Understanding Minors. Welcome, everyone. Today, we are going to begin a very important topic in linear algebra, understanding minors. Now, as you have progressed in your study of determinants, you have likely noticed that while calculating the value of a small 2x2 matrix is quite straightforward, calculating the value of a much larger matrix can become incredibly complex and time-consuming. To make this process more manageable, we use smaller, more manageable building blocks called minors. Think of them as the simplified components that help us break down a large problem into smaller, digestible pieces. It is also important to recognize why we are learning this. Mastering the concept of minors is not just an isolated skill. It is actually the essential first step toward mastering more advanced techniques, such as the expansion of determinants and the process of finding the inverse of a matrix. So, let's dive in and learn how to identify these building blocks. Definition of a minor. First, let's establish our notation. Suppose we have a determinant, which we will call delta, and this determinant is of order n. Now, how do we find a minor? Let's pick a specific element within that determinant, which we'll call a sub-I. J in this notation, the letter I represents the row number, and the letter J represents the column number. The minor of this specific element, a sub-I J, is simply the determinant you get left over after you delete the entire ith row and the entire jth column where that element lives. To keep our work organized, we denote the minor of the element a sub-I, J as m sub-I J. Before we move on to the step-by-step method, I want you to pay close attention to a crucial observation regarding the order of the determinant. This is a vital concept to remember. If your original determinant is of order n, the resulting minor, m sub ij, will always be one size smaller. Specifically, it will be a determinant of order n-1. To put this into perspective, if you are working with a 3x3 determinant, your minor will always be a 2x2 determinant. Similarly, if you start with a 4x4 determinant, your minor will be a 3x3. Always keep this reduction in mind as we move to the next slide to see the actual process in action. Now that we know why minors are so important for simplifying large matrices, let's dive into the formal definition. Step-by-step process to find a minor. Now that we have established the formal definition of a minor, let's break down exactly how you can apply this in practice. Finding a minor isn't a matter of guesswork. It is a systematic, 5-step process. First, you need to identify your target. Look at your determinant and pinpoint the specific element, which we call a sub-I, J, for which you want to find the minor. Step 2 and 3 are the deletion phases. Once you've identified your element, I want you to mentally or even physically strike out, or delete, the entire row I where that element lives. Immediately after, do the same for the entire column J, which is the column where your element is located. Think of it as clearing a path through the matrix. Step 4 is where you reconstruct the data. Look at the elements that weren't crossed out. Write them down, keeping them in their original relative positions to form a new, smaller determinant. As we mentioned in the previous slide, if you started with a 3x3, this new structure should now be a 2x2. Finally, in step 5, you perform the actual arithmetic. Calculate the numerical value of this new, smaller determinant. Once you have that final result, you have successfully found the minor, denoted as m sub I J. In the next slide, we are going to walk through a concrete numerical example to see these 5 steps in action. Illustrative example. Now that we have understood the definition and the systematic steps, let's put this theory into practice with an illustrative example. Take a look at this 3x3 determinant, which we will call delta. It consists of the first row containing 1, 2, and 3, the second row containing 4, 5, and 6, and the third row containing 7, 8, and 9. To demonstrate how the process works, we are going to find the minors for 2 different elements. Specifically, the element a sub 1, 1 and the element a sub 2, 3. Let's start with case A, where we are finding the minor m sub 1, 1. First, we identify our target element. The element a sub 1 is located in the first row and the first column, which is the number 1. Following the steps we just learned, our first task is to delete the entire first row. You can see here that the first row has been struck out. Next, we must also delete the entire first column. After performing these deletions, look at what remains. The remaining elements form a new, smaller 2x2 determinant. This is our minor, m sub 1, which contains the elements 5, 6, 8, and 9. To find the final value, we calculate the determinant of this 2x2 matrix by multiplying 5 times 9 and then subtracting the product of 6 and 8. This gives us 45 minus 48, resulting in a minor value of -3. Now let's try case B, finding the minor m sub 23. In this instance, our target element is a sub 23, which is the number 6, located in the second row and the third column. Following our procedure, we first strike out the entire second row. Then, we strike out the entire third column. By looking at the remaining elements, we can see they form a new 2x2 determinant consisting of 1, 2, 7, and 8. This is our minor, m sub 23. To calculate the value, we multiply 1 times 8 and subtract the product of 2 and 7. This leaves us with 8 minus 14, giving us a final minor value of -6. As you can see, the process is the same regardless of which element we choose. To help you visualize this deletion process even more clearly, let's move on to a real-world analogy in the next slide. Real-world analogy. Now, before we move on to some common pitfalls and wrap up our lesson, let's take a moment to step away from the numbers and look at a real-world analogy to help solidify this concept in your mind. Imagine you are looking at a seating grid in a large cinema hall, where every seat is organized by a specific row and seat number. Suppose you are asked to find what we might call the influence zone of a specific person sitting at row I and seat J now. Let's apply a specific rule. To find this zone, you must completely ignore everyone sitting in that person's own row, and you must also ignore everyone sitting in that person's own column. The group of people left sitting in the remaining seats, those who were not part of that person's row or column, would constitute the minor of that person. Just like we saw in our previous calculation with the 3x3 matrix, the value of this minor isn't just the group of people itself, but rather the mathematical result you get when you perform the determinant calculation on that remaining grid. This should help you visualize why we strike out the row and column to find the minor. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of minors, it is very easy to make small, careless errors that can lead to the wrong answer. Let's look at some mistakes to avoid. First, a very frequent error is confusing the element itself with its minor. You might find the element, let's call it a sub ij, and accidentally write that down as your answer. Please remember, the element is just the starting point. The minor, which we denote as m sub ij, is the value of the determinant of the remaining elements after you have performed the deletions. Don't stop at the element, you must complete the calculation. Second, watch out for incorrect deletion. When you are looking at your matrix, don't just cross out the single element you are focusing on. You must strike out the entire row I and the entire column J. If you leave the rest of that row or column intact, you aren't actually creating a smaller building block, and your minor will be incorrect. Third, be extremely careful with your arithmetic when calculating the final value, especially in 2x2 determinants. When you compute the result using the formula a times d minus b times c, the most common mistake is a sign error during the subtraction step. If you are subtracting a negative number, remember that it becomes addition. One small slip with a minus sign can change your entire result. Finally, keep an eye on the order of your determinant. As we discussed in our definition slide, the order must reduce. If you begin with a 3x3 determinant, your minor must be a 2x2 determinant. If you find yourself still working with a 3x3 matrix, you have missed a crucial step in the deletion process. Keep these points in mind, and you will find that calculating minors becomes much more reliable. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways to ensure you have a solid grasp of the concept before we move on. First, let's revisit the definition of a minor. Remember, the minor, which we denote as M sub ij, is simply the determinant that remains after you have removed the ith row and the jth column from your original matrix. Second, keep a close eye on the order reduction. This is a fundamental rule. If you start with a determinant of order n, the resulting minor will always be a determinant of order n-1. So, as we saw in our earlier examples, a 3x3 matrix will always yield a 2x2 minor. Third, let's summarize the process. To avoid any confusion, always follow this systematic flow. First, identify your target element. Second, delete its row. Third, delete its column. And finally, calculate the value of the remaining determinant. Lastly, pay attention to the notation. When you see M sub ij, it specifically refers to the minor associated with the element located at row I and column j. If you have mastered these points, you are well on your way to mastering more complex topics like the expansion of determinants and finding the inverse of a matrix. Great job today!